So today we're going to discuss complex exponential series. Now remember the last class we were discussing the trigonometric Fourier series representation, which was given as this equation, where our main task was to find the fundamental period, which would give us omega 0, and then to evaluate the AK and the BK. And that would give us then the Fourier series representation in the trigonometric, that is the sine and cosine format. Now, because we have Euler's identity, we can come up with another expression for this Fourier series. Again, these apply to only periodic functions, but we can come up with a different form of that. And this is the complex exponential series, where we use e to the j k omega 0 t, and as you know, this breaks up into cosine and sine, and then the ck are then evaluated. Okay, so it's a little bit more compact form. I'm going to skip the derivation because, you know, with some patients you could start with the trig series and end up with this. We're not going to do this. Now, for a moment, I would like you to pause and turn your textbook to page 109. So, if we want to get a relationship between the CK and the A and the B, we can use these equations in the text. 320, 323, 324, and then also notice 3.22. So I'm not going to write those down here. You can refer to those in the book. By the way, the CK are generally complex. Remember, we have this J in here. So you are going to, in general, get a complex number. And the C minus K, they're just related by the complex conjugate. Okay, if you recall the example, and again, we recapped it, we knew that A0 is equal to 0. And this was the expression for the AK, and then the BK was equal to 0. If we apply equation 323 to this, we get C0 equals A0, and CK is equal to 1/2 AK, and C minus K equals 1/2 AK. So that's how we would find the CK once we've already found the AK and BK. Now, what we usually do is we usually don't do this. We usually start with the exponential series, and we compute them directly. Okay, so this is how we compute it directly. So the next piece is going to be an example of that. Let's discuss what line spectra are. Here we're starting to introduce the idea of the signal spectrum. Which is a more general term. We find that for periodic signals, the signal spectrum takes the place of discrete lines. So these are usually defined using the complex exponential form. And the amplitude spectrum, there are two parts, the amplitude spectrum and the phase spectrum. But the amplitude spectrum is a plot of the amplitude, or the magnitude of CK versus omega. And again, omega is multiples of the fundamental frequency. So they happen at discrete frequencies. And then, because the magnitude, because they're related for negative k by the complex conjugate, the magnitude is the same. So it will be symmetric. So this value equals this value equals this value, and this would be the magnitude of CK versus omega. So that would be an example of a line spectrum. It's symmetric about the vertical axis. It's an even function of omega. The phase spectrum, on the other hand, again, because C k equals, or let's say it this way, c minus k equals ck complex conjugate. If we wrote this in polar form, the angles would be the opposite. So theta, this would be angle of c minus k. The angle of c minus k equals negative the angle of ck because of this complex conjugate relationship. So this one is an odd function. So let's say this were the k values. So let's say this is pi over 4 minus pi over 2. And so we'll get, let's say we get pi over 2 up here. So let's say we have this kind of a situation at our different frequencies. Then on the other side, it's just going to be the opposite. This one's going to show up down here. And this one is going to show up here. Okay? So it's an odd function. It's symmetric about the origin. The rest of this is just talking about how to get, if we move to the sine plus, the cosine with phase form of the trig series. Again, we can relate the ck to the 1/2 ak. So if you're starting with the trig series, it's 1/2 ak that you're plotting. And finally, the last two pieces here, I will show you some MATLAB files, probably in class. Well, I'll do this with the trig series in class, and then it's the same for the complex exponential series. But again, when you truncate the Fourier series, we get this Gibbs phenomenon, which we saw with the trig series. Is, let's say it's a square wave, and say it looks like this. So at the transitions, you get some ripple. So that's the Gibbs phenomenon. And this has to do with power, and we're not going to really discuss it, but this is kind of a measure of the energy in the signal, the average power, I should say the power in a signal, and we get that by absolutely squaring the ck and adding them up over infinity, and this gives us some kind of a measure of the energy in the signal. Okay.